Philipp Kuhn. I work at the Regensburg site in Germany, and I'm responsible for the R&D of this legacy gene art portfolio. So it's gene synthesis, protein expression services. And super happy to be here. I feel very welcome at this conference and also in this Antibody community. It has been super nice. So what I'm going to talk about is how we as Thermo Fisher do help our customers to fulfill their goals. That's our mission. We're all at the core scientists, helping our customers to fulfill their scientific purpose and to make the world healthier, cleaner, and safer. And what I will go through is to talk a little bit about challenges in antibody therapeutic development, but I mean, you all know this. We've gone through all of this in many talks, many great talks over the last 2 days. And then I'm going to explain to you what is synthetic biology and how can we help to streamline some of those challenges or to solve some of those challenges for you. There's 2 things which are important, which is fast access to a lot of DNA, de novo synthesized DNA, but also it's really important that the cloning strategy is set up in a way that it's efficient and also reliable, right? If I still have some time in the end, I might be talking about our expression services. Probably won't get there, but let's see. All right, so if you look at the whole journey to develop an antibody, there's many stages, there's many chances for failure. So it's important to go through these as efficiently as possible, and then there's, of course, new methods need to be developed. I mean, we've heard about it in many talks. It's really important to minimize the failure in later stages very early. And I also learned that there is a focus on a lot more complex targets, a lot more complex formats, and so on. And this is really where we would like to help. And I'm going to focus today a little bit more about the optimization phase, not so much about discovery and all the clinical work that we also do support in Thermo Fisher. Yeah, so if you look at this, and I think, I mean, it's just amazing. I mean, what everybody is doing, you know, working on this multi-parametric challenge to optimize many different traits of an antibody at the same time. In the end, it's still, in my view, it's the same DNA sequence or the same amino acid sequence. Everything is influencing each other. And some point after like going through all of this, maybe by bioinformatics tools, AI, you want to test your antibody, right? And you want to do this quickly, you want to do your next iteration. So you want to have fast and reliable access to de-risk your lead candidates, and that's where synthetic biology can help. So what is synthetic biology? It marries the engineering principles with biology. I'm originally an engineer, and I really love it. It's going through rapid design, build, test cycles very quickly to build novel biological systems that have not been possible before or basically not existing in nature. For example, antibodies with traits that are just not naturally anymore. And for this, we do have services for synthetic DNA, plasmids, and also protein expression. We also have tools for gene editing, of course. And this can all help to go and do synthetic biology for antibody development. There are many different application areas, and I think they're all profiting from the progress where synthetic biology is applied. Of course, there's a lot happening in biotechnology with plants and new materials and things like this. There's also new things happening in personalized medicine, neoantigen therapies, and so on, of course, especially after mRNA therapies were so successful. But of course, we talk about therapeutic antibody engineering today. And I would like to go a little bit more into the technical things by showing you how the gene synthesis process works and what we have been working on to address basically capacity bottlenecks within our manufacturing to be able to serve a lot of customers at the same time, but also, yeah, to do this very reliably. So when you order synthetic DNA, we usually do some codon optimization to have optimal expression. We have our gene optimizer software, which has been shown to be superior to really get you the best expression yields possible. And then we break up the target insert into oligonucleotides. And this has been historically really the bottleneck for us, but we have been investing a lot of time and resources into developing a microchip-based platform, and I'll show you a little bit about this on the next slide. But also it's important that you do think about how can I efficiently design my cloning strategy and how can I prepare to do many, many different assemblies in parallel, but also again and again. And I'll show you a little bit what we do internally in a lot of cases and discuss a little bit the pros and cons of different approaches. I'm not going to talk about NGS, but of course it's very important if you have to sequence many thousand clones every day. So this is our high-throughput synthesis platform that we developed and we use internally. We decided it's time to go away from a 2D surface to synthesize oligonucleotides and do it in 3 dimensions. So we use those small microbeads. They're porous and give us about 1,000 times more surface area where we can synthesize oligonucleotides very efficiently, but also create a lot of material. It also has the advantage that those oligonucleotides are bound to beads and we can manipulate them very easily by creating small gas bubbles at an electrode and basically pop them out, then bring them together, all the oligonucleotides that assemble a gene together. And this is a completely automated process. We designed instruments for this, and it really helps us to synthesize all of the thousands of genes that we get all the time and make sure everybody gets their products delivered in time. And yeah, has been quite a cool project. Been working on this for a while. So if you have any questions later on the bus maybe, or just drop me an email. So if we now switch gears and look a little bit at antibodies, I'm not going to explain again how an antibody looks like. I think we have heard this a lot of times. Just want to talk a little bit how to translate the amino acid or like the structure into DNA and into the open reading frame, so we can see there's constant regions and variable regions. And for me, this is a little bit like working with Legos. Yeah, so you have basically only a small bit of each chain for a standard IgG that needs to be de novo synthesized. So once you fix your constant backbone or like your constant part of the antibody, there's really no need to resynthesize everything again. So I'm going to explain a little bit how we do this for our customers who onboarded their constant parts with us, and how you could also do it in your own labs. There's, of course, many different formats. I learned so many more, and we do have experience working with those, but it's really just to show here the slide is it's basically the same principle, right? You have a plasmid backbone, you have your constant parts, and it's really, in most cases, really worth the effort to really decide, okay, will I clone into the same constant region over and over again and repeatedly, and should I invest a little bit of time in the beginning to prepare for this, or will this change all the time? So, exactly. So to efficiently clone and drop variable parts into a plasmid that has those constant regions, in my view, there's a lot of different cloning technologies and strategies and so on, but if you want to work with a seamless technology, synthetic biology research and all of those developments have yielded basically 2 technologies, which are, in my view, very nice. We have kits for this from Thermo Fisher if you want to try them. One is type 2S cloning, also known as Golden Gate cloning, and one is Gibson cloning or assembly. We actually prefer for antibody development or for those challenges that I just mentioned, type 2S cloning. If you work with Gibson cloning, it's very flexible. It gives you a lot of opportunities to be fast and to switch around. But the problem is that it usually relies on a linearization of the vector by PCR. So just make sure that you sequence your the whole plasmid after you did this, and not only the insert, because you might introduce some errors there, and then you won't have any expression in the end. Or yeah, basically you have to redo all of your cloning experiments. So if you already know you will use this vector over and over again, we think it's much better to use type 2S cloning because it's also seamless and fast. You can do multiple fragments. It's also very flexible. And you can prepare the vector, you can QC it, you can stock it, you can just take it out in your reaction. It's ready to go. And one of the disadvantages is usually also that you have to make sure that there's no restriction enzyme sites in your insert or in your vector. We of course can mitigate this by our codon optimization that we usually do for antibodies anyway. So we can also remove those in the insert. Okay, so how does it work? We take a vectors, we know what is the constant part. I mean, customer will tell us, and then we do a de novo synthesis of this. We add a selection cassette and restriction sites, and then we only have to do this once, and then we have the vector on stock, and then it's ready to go. You can go into a website and you select your vector, and you can drop in your sequences, which are de novo, and then we can do this, of course, hundreds to thousands of times just to exchange the variable region and rapidly clone into this prepared vector. Yeah, and assemble the full constructs. The nice thing is that this works very fast and efficiently, so we don't have to go through any other production vector or whatever. And here's just some examples from data that I pulled from our manufacturing, where customers have onboarded different, basically light chains, heavy chains, constant parts, and you can see they're all like between, let's say, 300 to 400 base pair as expected, and it gives you really the opportunity to be very fast. And you can see I'm German. I'm not going to put 100% here. It's we work on this all the time, and I think it's a very fast process. You can get your final clone in your vector with your constant region in 8 days, and we can produce thousands in parallel, and it's a very cool process. And I mean, of course, you can do this also like this in-house and use linear fragments to work with this. A lot of customers do this as well. Just one word about the expression services. So if you ever get to a capacity bottleneck in your lab, we can also express antibodies in different scales, from small scale to larger scales. We do use our XP systems from Thermo Fisher. We've been working very closely with the folks in Frederick who developed this. And you get like this whole, I would say, ecosystem of reagents with those cell lines, transfection reagents, media, and so on. And then you can go back and forth between the service from at our side and then also in your lab. We've been working a lot on small-scale expression recently. I'm just going to show very quickly that we have quite good or quite low variation between plates, different tested a lot of different antibodies that express in various different titers. And then also if we do same antibody over the plate, we also see that the process is very stable and we get very good recovery. So if you have interest in this, you can also talk to us at the booth and so on. Yeah. Good, I'm just at time, so thank you.